Hi and welcome to Pre-Calc 30 with Miss Verity. Today we're going to be starting section 5.1, which is trigonometric functions and graphs. So we spent the last unit looking at different trig functions and their values using the unit circle. This unit is going to be spent graphing them. So we're going to start today by graphing sine and cosine functions. So sketching graphs, sine and cos, demonstrating understanding of the effects of vertical and horizontal stretches. Remembering that vertical stretches are our A values, horizontal stretches are our B values, and then solving a problem by analyzing the graph. So we have our trusty unit circle, which you guys know how to use your special triangles, which is excellent, and our stripper rule. So our basic sine graph, we will talk about a little bit later. We'll hold on, we'll come back. Characteristics of sine and cosine. So they are what's called periodic functions. So a function that repeats itself over and over and over and again. Basically, if we weren't to give this a domain, it would repeat itself for infinity. The period of a function is the length of the interval of the domain over which a graph repeats itself. So the period is sort of one revolution, and then it would start to repeat itself. The amplitude of a function is the vertical distance from the midline, and a sinusoidal curve is the name given to a curve that fluctuates back and forth like a sine graph. So sine and cosine graphs are sinusoidal functions or periodic graphs. So there's kind of the look. So as we go around the unit circle, we know that we get positive and negative values for our functions. I mean, that's what a sine graph and a cosine graph look like as they repeat themselves around the unit circle. So sine of x. So there's our basic look. We've got a period of 2 pi, an amplitude of 1. So some basic things. The maximum value for a base sine graph is always 1. The minimum for a base sine graph is always negative 1. It has an amplitude of 1, the amplitude being the point from the midline to the maximum, or you could also say from the midline to the minimum. That would also be an amplitude. The period is 2 pi. So the period being, well, if our graph starts at 0, well, as we go along, it doesn't look the same again until we get to 2 pi, and then it would start to repeat itself. That's an example of what the period is. The y-intercept of a sine graph is 0, and the x-intercepts on the given domain are negative 2 pi, pi, 0, pi, and 2 pi. Basically, they are intervals of, like, pies. So it would also happen at 3 pi, negative 3 pi, 4 pi, negative 4 pi, etc., etc. In general form, we've got pi plus or minus pi n, where n is an element of the integers, and that's the general form for x-intercepts. And then the domain is x is the element of all real numbers. If we don't restrict it, this graph would go on forever and ever and ever and ever. And then our range, again, range is the y's, our maximum being 1, our minimum being negative 1, and in between there, they can be anything. Cosine graph is pretty well the exact same as a sine graph with a couple differences. One of the main differences is that the y-intercept is 1, not 0, and that the x-intercepts happen at intervals of pi over 2 plus pi. So rather than being pi plus pi n, it's pi over 2 plus pi n. So negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, etc., etc. Domain's the same, range is the same. So example 1, graph each function for the given domain and use the unit circle in your table of values. We'll use our special triangles in a table of values because we know that, back in grade 9 when you first learned to graph, the easiest way to graph is with a table of values. So if we pick the values that our graph gives us, so if we've got x's, I'm going to go all the way along, and we've got y's, well, our x values that we're given are negative pi, negative 3 pi over 4, negative pi over 2, negative pi over 4, 0, we've got pi over 4, pi over 2, We've got 3 pi over 4. We've got pi. We're going to run out of room. 5 pi over 4. 3 pi over 2. And then our last one will also have 7 pi over 4. But if we go to our special triangles, and also looking at our quadrants, some important things, we know we've got 0, pi over 2, we've got pi, 3 pi over 2, and we've got 2 pi. Well, coordinates of our points are 0, 1, negative 1, 0. At 3 pi over 2, we've got 0, negative 1, 0 and 2 pi, we've got 1, 0. And then because we're given pi over 4 values, that is just our 1, 1, root of 2, 45-degree triangle. So with our sine graph, we're looking for, if we're at pi, what is our sine value? Well, if we're at negative pi is right here. Our sine value of negative pi is 0. That is negative 180. The sine of negative 180 is 0. Negative 3 pi over 4, things we need to check. Negative 3 pi over 4 has us right there. That means we are in quadrant 3. If we're in quadrant 3, what is the value, positive or negative, of our sine function? Well, it is negative. Well, and our reference angle is 45. 45-degree reference angle is root of 2 over 2. At negative pi over 2, we are right here. Sine of that is negative 1. At negative pi over 4, we're in quadrant 4. Our sine is still negative, and reference angle, we are root of 2 over 2. Sine of 0 is, that is this value right here. Our sine of 0 is 0. Pi over 4, we are in quadrant 1. Our sine is going to be positive, and that is root of 2 over 2. Pi over 2 has us up top. Our sine of that is 1. 3 pi over 4 has us in quadrant 2. We are root of 2 over 2. The sine of pi is 0. Remembering, again, in all of this, if we're using the coordinates of our unit circle, sine is always our y value. And then with this sort of x being what, this is our angle. And it's just asking, what is the sine of that angle? Well, sine of 5 pi over 4, that has us back in quadrant 3. That's negative root of 2 over 2. 3 pi over 2 is negative 1. And that last point we're going to talk about, 7 pi over 4, that is negative root of 2 over 2. And so, again, basic idea, back in grade 9, we're going to plot those points. So we've got negative pi and 0. Our negative 3 pi over 4 is root of 2 over 2, and that as a decimal is about 0.707. So just a little bit over half. Root of 2, we're at negative 1. And if we keep going, if we plot all of those points going until 2 pi, because that's what our domain is, we get a graph that looks like that. All right. So now if we want to graph cos of x from negative 180 to 540, key things to note, we are in degrees, so that's kind of nice. It's a little bit hard to read here on the board, but same thing if we do our x's and our y's. Well, we're given intervals of 90 degrees. So we have negative 180 degrees, negative 90, 0, 90, 180, 270, 360, 450, and and 540. All of these values happen to be ones that are on sort of our grids of our coordinate plane. And so again, we've got, this is 1, 0, 0, 1, negative 1, 0, 0, negative 1. With cosine, we are looking at the x-coordinates of those points. So the cosine of negative 180 is negative 1. Cosine of negative 90, remember cosines are x-coordinate, that is 0. Then we're at 1, 0, negative 1, 0, 1, 0, negative 1. And if we want to plot those points, here we go. Negative 180, 270, 360. And so if we were to graph those, and again, if we wanted to continue on, they would repeat that same pattern again and again and again and again and again and again and again. But that's what a basic cosine graph looks like. Pretty well, it's the exact same as our sine graph, except the main difference is our y-intercept is at 1, not 0. So exploration, grab your Desmos, and I want you to graph those functions. I'm not actually going to type them in, but I'm hoping that you'll actually look at them because then you can see what happens to the graph. But group 1, remember we've got our base function, and group 2, same, our base sine function. In this case, we are adding a values. And if we know from all the other explorations we've done, a values of graphs are going to be a vertical stretch. And if we think about a sine graph or a cosine graph, if you are stretching it vertically, you're going to make it go like way more up and down. What that's going to affect is your amplitude. And then in group 2, we've got a bunch of b values. Well, b values, what we know, those affect our horizontal stretches. Which when we're talking about sinusoidal functions, that is going to affect our period length. So today our basic transformations, we're just talking about a's and b's. So for sinusoidal functions of the formation a sine bx or y is equal to a cos bx, a is a vertical stretch by a factor of a, and b represents a horizontal stretch by a factor of 1 over b. So remember, if our b is 2, that means our stretch is 1/2. If our b is 1/4, that means our stretch is 4. So using the features to sketch the graph of the sinusoidal functions, if a is negative, you have a reflection across the x-axis. So the amplitude is a. The period of a function is 2 pi over b or 360 over b. So some things to note, if your b value is greater than 1, so things like 2, 3, 4, 8/5, those are all values greater than 1. That is going to shrink the period. It's going to compress our graph. It's going to squish it closer together. If you have a b that is greater than 0 but is less than 1, that is not written correct. Wow, let's try that again. If your b is less than 1 but greater than 0, so that's things like fractions. 1/4, 1/3, 2/3, 3/4. That is going to stretch the period or make the period longer. And then also the coordinates of vertical and horizontal intercepts. All right. So example 2, state the period in radians and the amplitude of each trigonometric function, then write the equation of the function. So a couple things we want to find the period. So the period happens when the graph starts to repeat. So really you can check any spot. So if we started there, the look when we would repeat our function would happen right there. So from 0 to 3.14, well, that is pi, period. But you can really look anywhere. You don't have to look at those points. Like I could look at this point, well, my graph starts to repeat right there. I could look at this point, my graph starts to repeat right there. You can pick any point as long as you find the repeating point. So things we know is that the period of a function in radians is equal to 2 pi over b. Well, if we know that our period is equal to pi, we can solve for what our b is. So if we multiply both sides by b, we get pi b is equal to 2 pi. And if we divide both sides by pi, b is equal to 2. That means we have a horizontal stretch of 2, which would mean our period is going to be half as large. And then the next thing we want to check is we want to find our amplitude. So this graph, when we look at it, I'm going to erase some of my scribbles on it. Our y-intercept is at, that looks like 1.5. Nope, that's at 2. Just kidding. So normally, our y-intercept, this is going to be a cos graph because it has a y-intercept that's not 0. And the fact that it's at 2 tells us we have a vertical stretch of 2. Another thing to look at is right there is our midline. That's kind of where it divides the graph in half. Well, there's 2 units from the maximums to the minimums. So that means our A is going to be 2. Well, if we fill this into our graph, it's going to look like y is equal to 2 cos of 2x. Maybe putting it in brackets might help. You don't necessarily have to when it's just like that. Looking at our next function, this one, our y-intercept is at 0. That tells us we are going to be dealing with a sine graph. So if our y-intercept is there, we have a midline, and from our maximum to our midline is 3 units. So that's going to tell us our A is equal to 3. And then we want to find a repeating point. Well, if I like to use the y-intercept, I find, or x-intercepts, any variation of those, I find that the easiest to find the repeating point. So here we're going up, and then we go down, we hit a minimum, we go back up. Well, at this point, we start to go back up again, we hit a maximum. That would be a repeating point. So from there, the numbers are really hard to read, but this says 12.56. Well, to figure out what that is in radians, we know radians are in terms of pi. So if we divide that by pi, that's going to tell us that we have 4 pi units. So this whole thing is 4 pi. Well, normally, if we know our period is 4 pi is equal to 2 pi over b, multiply both sides by b. 4 pi b is equal to 2 pi. Well, if we divide by 4 pi, we're left with b is equal to 1/2. And that's what we would expect because our period is large, it's twice as large, that our b would be 1/2. So this graph is y is equal to our a value, which was 3, sine of 1/2 x. So example 3, sketch the graph of y is equal to cos 3x from 0 to 360 using a table of values and mapping notation, comparing the graph to the graph of y is equal to cos of x, state the period and the amplitude of the function. Well, with this, things we know, we have a value of 1. If there's nothing written there, there's value sitting out there. So if we don't have any change to our a value, that means our amplitude is still just going to be 1. In this case, we have a b of 3. So that tells us our period is equal to 2 pi divided by 3. Or, I guess we're doing it in degrees. So period is equal to 360 divided by b. So our period is equal to 360 divided by 3, which is 120 degrees. So our graph is going to be repeating in terms of 120. Well, if we wanted to have our base values, so for our cos graph, we're going from 0 to 360. So in terms of 90-degree intervals might be quite nice. So this is our basic cos of x graph. We know that our cos of 0 is 1, cos of 90 is 0, cos of 180 is -1, 0, and 1. Well, things we can use, we can either translate each point, or we can use our mapping notation, where our points would be, so remember, our mapping notation is 1 over b x plus h, comma, ay plus k, and that's in brackets because those are points. So for us, our b was 3, so x over 3, or 1/3 times x, plus we don't have an h, so plus 0. Our a value is 1, so it's just y. So these points would become, well, 0 divided by 1/3 is 0. Our y's stay the same. 90 divided by 3 is 30. Our 180 divided by 3 is 60. 90, and then we have 120, and those y values stay the same. So if we're going to graph this, so there's a nice coordinate for you. Things we can do, we could split them into, we probably want to do 30-degree intervals. So 30, 60, this would be 90, 1, 2, so every 3, 180, that is going to be 270, 1, 2, 3, 360, and we need to graph from 0 to 360. Notice I didn't write down, so if we graphed our original, so I'm going to graph our sine of x function, and that's going to look something like, I'm going to do this as, just because I want to stretch it out a bit more. There's our 1. So remember, just kidding, we're doing cos of x. So our 1 value, and if we do the same, because remember you need to keep the scale the same. You can make the scale whatever you want it to be. Like you could have put your 1s right there, but that's going to be a very squished graph, and that's not ideal. So 180 was -1, 270 was 0, and 360 was 1. So our base cos graph look something like that. So that is what we had in our original interval, and we are going to graph the other one. So I'm going to graph it in blue. So same thing. So 0 and 1, these were 30-degree intervals. So 30 was 0. We had 60 was -1. We had 90 was 0, and 120 was 1. So if we were to graph this, well, notice we haven't actually filled in the graph to 360. So the key thing is if the domain says 0 to 360, you have to fill in all the missing pieces. Well, the nice thing about a sine graph is those patterns are just going to repeat over and over and over again. So in our 30-degree intervals, we're going up and down. So there is what our cos graph looks like in the interval from 0 to 360. So our period, notice, is the here to here. That's where it starts to repeat. That's our 120 degrees. So example 4, given 2 sine 1/2 x from -pi to 4 pi, identify the key features of transformation, use these to graph the function. Well, in our graph, we have an a of 2, which means our amplitude of our graph is going to be 2. We have, if our normal maximum value, it normally was 1. Well, if we're stretching it twice as much, it's going to be at 2. Minimum value, same thing, it's normally at -1. If we're stretching it twice as much, it's going to be at -2. We have a b value of 1/2. So again, if we have 2 pi, because we're in radians, divided by 1/2, well, that's the same as, if you want to rewrite it, remember fractions aren't scary. So this is 2 pi over 1, which would be 2 pi over 1 times 2 over 1, which gives us 4 pi. So our period is 4 pi. Our x-intercepts, because we're just stretching, those are still going to be the same thing, because 0 times anything is still going to just be, oh, just kidding, we do have a vertical stretch. Normally they are at 0, pi, etc., etc., etc. But because we're stretching them, they're going to be twice as much. Our intercepts, if we're going from negative pi to 4 pi, are going to be 0. Well, if it's normally at pi, if it's going to be twice as much, it's going to be at 2 pi. And if it's normally at 2 pi and you're stretching it twice as much, it's going to be 4 pi. Our y-intercept on a sine graph is 0. Well, 0 times your a value is still going to be 0. Our domain, well, because we have it restricted, I guess x, however you want to write it, everyone writes it different. We have negative pi is less than or equal to x, which is less than or equal to 4 pi. But in there, x can be anything. The reason we have that domain is because we restricted it. If it's not restricted, it would be element of all real numbers. And then our range, well, our y is going to be less than or equal to 2, but greater than or equal to our minimum, which is negative 2. In between there, y can be anything. So if we want to graph this graph, we need to go to 4 pi. So if we have 0, how many can we fit on here? Pi over 2. Let's go pi. 3 pi over 2. Then we'll go to 2 pi. 3 pi. 4 pi. So 3, 4, 5 pi over 2, 6 pi over 2, and 7 pi over 2, and then we have 8 pi over 2. And we have to go back to negative pi. So we're doing intervals of 4. So again, your table of values might be a good idea to use. This is going to be pi over 2 right here. And if we were to graph this in terms of table of values, if we want to use our basic ones, so we can either go back to our cosine, or sorry, we're looking at a sine graph, so that original example 1, things like we can use negative pi, let's use negative pi over 2, 0, pi over 2, and then let's go to pi. Let's see where that gets us. If we want to plot more points, we can. So we start, pi's are zeros, negative 1, 0, 1, 0. So again, the sine of negative pi is 0. And if we want to use our mapping notation, so for this question, our mapping notation, we had a value of 2 and a b value of 1/2. So, I mean, that's going to say 2x, we don't have a stretch, and 2y. The reason I got that 2x is because we have x over 1/2, which is just 2 times x. And so all of these points are going to become, well, negative pi is going to be negative 2 pi. 2 times 0 is still 0. We have negative pi over 2 times 2 is going to give us negative pi. Negative 1 times 2 is negative 2. 0 times 2 is still 0. 0 times 0 is 0. So that's a fun one. We end up with 2 times pi over 2 is pi. And 1 times 2 is 2. pi times 2 is 2, 0 times 2 is 0. So within our graph, if we're just going to graph our new one, so negative pi over 2 isn't on our graph, we're at 0. We have negative pi is at negative 2, so 1, this is negative 2, 1, 2. So at negative 2, we're at pi, 0, we're at 0, pi, we're at 2, and, oh, this last one should be 2 pi. 2 pi, we're at 0. Well, if we keep following that pattern, if we're going another pi gets us to the next point, so at 3 pi, we're going to be at negative 2. At 4 pi, we're going to be back at 0. And so our graph looks something like this, versus the original would look something like our normal pi over 2 value has us at 1, so we would normally look something like there's one period of a normal sine function, so it's twice as big. Example 5, given y is equal to negative 1/2 cos of 2x, identify the key features of the transformed function, use these to graph the function, etc., etc. So with this graph, our a value is negative 1.5, which means our amplitude, it doesn't matter what distance is it, like we're looking for the absolute value of it basically, so it would be, our amplitude would be 1.5, doesn't matter if it's reflected. Our maximum value is going to happen at 1.5. Our minimum is going to happen at negative 1.5. Again, that comes from our normal maximum value, which is 1 times our amplitude of 1.5. Our b value is 2. Well, then our period, and we're doing this in radians, I believe. It doesn't tell us, but let's do it in, well, let's do it in degrees. Why not? Normal period value is 360. When we divide that by 2, we are now at 180. The x-intercepts, those normally happen at pi over 2. So they're normally pi over 2, but we are stretching them by 1/2. So this means they are going to happen at, so we're stretching them by 1/2, they're going to happen at pi over 4 now, so that's pi over 2 times our vertical stretch, and that's going to be plus or minus intervals of pi. So our intervals are always usually plus or minus 2 pi. So things we're going to have, our x-intercepts are going to be 45, 135, 225, and 315. I don't think it's giving us a domain, so that's okay. Y-intercept, so normally it's at 1, but we have an amplitude of 1.5, so it's going to be at 1.5. Domain, in this case, there's no restriction, so x is the element of all real numbers. Oh, this one's actually, sorry, it's going to be y.5. We have a negative reflection. And our range, y is going to be less than or equal to 1.5, but greater than or equal to 1.5. Other than that, y can be anything. So to graph this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because we are condensing our domain, I'm not going to do it as far, so we're going to do pi over 2, pi, add another 90. Oh, we're in degrees, classic. 90, 180, 270, next one would be 360, and that's already going to give us 2 full cycles. So then if we have a half, 1, negative 1.5, half, 1, positive 1.5. In this case, again, remember our normal fun values were, we have our x-intercepts of 45 degrees. So we know in terms of 45, which is pretty well going to be every other one of these. There's going to be our coast graph. Those are our x-intercepts. As we keep graphing our maximum, well, in this case, we have it at negative 1.5. At 90, we'll be at 1.5, 180, and when we come back up. So our graph is going to look something like that. If we wanted to go to 360, I guess, there would be our graph. Perfect.